Chaotic systems are characterized by their sensitive dependence on initial conditions, which makes them inherently difficult to model and control. However, chaotic systems appear all throughout nature on many different scales. Recent studies have shown underlying chaotic structures in turbulent flow, the orbits of comets, and the dynamics of the heart. Avoiding or suppressing chaos limits our ability to control these systems, and in our recent paper we present a data-driven method that leverages the inherent sensitivity of chaos to achieve low energy stabilization of chaotic structures. In our paper we consider the three-body problem, where attractive forces between two larger particles, the Earth and the Moon, govern the motion of a third particle, a spacecraft. The three-body problem admits three unstable saddle points, shown here in red, and two stable equilibria. Orbiting around these unstable equilibria, we find recurrent chaotic trajectories, known as unstable periodic orbits, or UPOs. Infinitely many UPOs exist in chaotic systems, and the Lyapunov family shown here is just one of many. To study these UPOs, we can use a Poincaré map F that describes successive crossings of a surface of section sigma transverse to the flow. Importantly, a UPO x bar appears as a fixed point of this map. Our goal is to learn a Poincaré map F, and we simulate various trajectories recording successive crossings of the surface sigma. Using this data, we can express successive crossings in terms of a library of polynomial terms theta and a sparse matrix of coefficients z. We find z by solving this sparse regression problem shown here, known as the Cindy algorithm. This gives us an analytical expression for the Poincaré map F. Using the linearised map A, we now find a controller K that satisfies this Lyapunov expression. This is known as a pole placement problem, where we move the unstable eigenvalues from outside the unit circle inside by solving a convex semi-definite program. We add a constraint on the decision variables, which causes the magnitude of the eigenvalues to increase. Our controller applies small, locally optimal velocity impulses at the crossing of the surface sigma, which aligns with the local stable manifold shown here. The blue controlled trajectory remains on the UPO's path, whilst the red uncontrolled one leaves quickly. Our method is a data-driven, sample-efficient, interpretable, and low-energy method to stabilise UPOs. There are a large range of potential applications, ranging from robotics and spacecraft control through to fluid flow control.